Yeah, I think it works.
Okay, perfect.
Awesome. Yeah, we're good. We're live.
Awesome. Cool. Yeah, we'll just give everybody just maybe a couple seconds before we kick this off. But yeah, happy Saturday, everybody. Thanks for tuning in if you're on YouTube or on Discord.
Hey, Suchi.
Hello.
Hey, Suji.
Hello, everyone. Um, I assume you're waiting for the rest of my group to join. Um,
Yeah, a lot of people are filing in right now. We're just admitting people. Do you want me to promote you to co-host just so that you could share screen, or would somebody else from your group want to do that?
it was somebody else from my group. It was Sharma, and
Yeah,
I don't
Charles.
see. Oh, it was Charles. Oh, sorry, my bad. I do see Charles in the list of attendees, so you can promote him.
Okay, sweet. Just added him to co-host. But yeah, thanks for being able to talk about chapter 6. This is for anyone that's watching on YouTube, this is model development and offline eval. So pretty hot topic with all these models coming out. How do we evaluate them? So I assume you all will be giving us all of the wisdom about all of that today.
Cool. Yeah, it's an exciting topic. So um, we're glad we got this chapter.
Cool.
Should I go ahead and present it?
Yeah, absolutely. Yeah,
Yes.
we'll go off mute and yeah, feel free to present. But thanks again for being able to present this week.
So, um, sorry, it's not showing up the tab. Give me 1 second. Awesome.
Cool. So let's get started. Okay, yeah. So hello again, everyone. This is Group 4, Team Cricket. Um, I'll be back with an explanation of that name in a minute. So today we are presenting chapter 6 of the book, and yeah, so we are actually the merged version of two different groups, and both of our former groups were rather quiet, so we decided to call ourselves Team Crickets. I'm Suchi. You have seen me last week as part of the host team, and this week I'm presenting for the chapter. Um, I'm most recently at Meta. Previously been at a couple of different hardware and software roles, also associated with Georgia Tech. Let me pass this on to Sharma, who is also on our team.
Hey,
Is he on?
yeah. I guess you can hear me. Yeah. So, I'm hey, I'm Sarma. So I've been working in the industry for a while. I work at Amazon right now. And yeah, I've been doing machine learning stuff. Yeah, that's about it.
My name is Charles. I'm a MLE at Verily, also known as Google Life Sciences. Been working on developing ML models, infrastructure, and most recently working on applied large language model research. Been working here for about 5 years. And that's about it.
Cool. Yeah, that's all of the presenters today. We do have a couple more group members who aren't joining today, I believe. So can we move on to the next slide? Cool. So we'll start with the chapter summary, just sort of a TLDR. So the nice thing is this is the fun part of ML. This chapter deals with ML model selection, which is sort of the heart of ML, right? So this chapter will go on to talk about how to select models for your task, different aspects of model development, including ensembling, and also talking about how to track inversion experiments, a little bit about distributed training, and finally about how to evaluate models. We have added a couple of key takeaways here. This is more of a personal takeaway from our team. What we found interesting about this chapter. So the first thing we realized is that models are like code, and they need to be evaluated in the context of the theory and the business domain. And this is a recurring theme in the chapter, but also in the book. And similarly, models at scale require a different set of skills to train and manage compared to a small model. This we thought has parallels in databases, and we also noticed that engineering leadership might need to understand how scaling works, like they typically do for backend systems. For the last part, one of the interesting things we noted was model testing includes an online and offline component. So offline eval is not a substitute for online performance. So you do need to do both. So we thought those were the highlights for the chapter. Can we move on to the next slide? We will be diving deep into each of these aspects going forward. So the first part of the chapter was model development and training, and the second part was eval. So let me start with evaluating ML models. So the idea of evaluating ML models is, given an ML task, what model should you use for it? Obviously, given unlimited time and energy, you will eventually find the optimal solution, but that's not the point here. The point here is that in production, there's always a cost associated with developing the model. And so the idea, and as we know in industry, all models solving a business problem have the same constraint. They were needed yesterday. So, and then the chapter section goes on to talk about, how current ML is split into neural networks versus classical ML, but classical ML still stays relevant for many problems. And knowledge of common ML tasks is essential to actually go about evaluating which model is ideal for your task. Next slide. So a couple of different things to consider while evaluating the trade-offs. In real life, other than model performance, you might want to think about explainability, resources, like in terms of compute, cost, memory, and so forth. And also remember that depending on which model you use, you're looking at differences in many different aspects, right? From data collection process to deployment to training pipeline to everything. So we do have an example here that sometimes you might have a model that has a lower accuracy, but it needs, if it's faster to train, it's interpretable and easier to deploy, maybe that's your preferred model in that situation. Moving on to the next slide. So Chip had these really cool tips for model selection. So the first tip was avoid the state-of-the-art trap, which is basically, state-of-the-art means that the model performs better on some static data sets, but in production or in your specific use case, that may not apply. The second and super valuable tip is start with the simplest models because they're easier to deploy, debug, and at worst, they provide a baseline for evaluating your complex model. Avoid human biases, and it should go without saying. Evaluate good performance now versus good performance later, which also is a pretty valuable idea in that, you want to account for potential future improvements and validate that improvements are even possible, but you do want good performance now. And as always, you have to evaluate your trade-offs. It might be the trade-off between false positives and false negatives. It might be compute versus accuracy trade-off and so forth. And the last but not the least is understand your model's assumptions, the theoretical assumptions of your model, and see whether your data satisfies them. Can we move on to the next slide? So while we were going through this section, we thought that this had parallels with general software engineering. For instance, the first principle, don't use something just because Google did it, right? So in software, you would typically say, don't use the latest framework just because Google did it. In ML, you would say, don't use the latest model just because Google published a paper using it. And similarly, for establishing a baseline, in software, you would typically start with a POC first. And in ML, similarly, we should ideally start with a simple model first. For the third point, don't bike shed something from experience or preference. This is the human biases part of it. We tend to do this for frameworks or languages in software. It's the same with ML. When you're choosing a model or architecture, you should ideally not just go from experience or preference, but look at the specific problem and what it requires. Can we move on to the next slide? Next slide, please. I think you went one too far. Sorry. That's one. There you go. Deploying the best now versus optimizing for later. Obviously, in software, we tend to deploy the best code now rather than optimizing for later. It's the same with models. Trade-offs, of course, that's true for software as well. Is this feature something that will change later? How many boxes do we need? Things like that. Versus in ML, it's like, do we care more about false positives or false negatives? Does this application need a GPU? Things like that. For assumptions, in software, we tend to say understand your tools well before you commit to them. And with ML, it's the same thing. Understand your model well and the assumptions and the theoretical assumptions before you commit to it. Yeah, next slide. With that, we'll have a quick poll started about your experiences in choosing model. We just want to get a sense of which models tend to be most used in industry versus academia by different people. So that's the poll going on. And while that's up, I will be talking about a case study. Just a second so that okay. Cool. So this case study is from my work. So this was a particular situation where we were trying to predict relationships between users in a network, and this is essentially a classic use case for a graph neural network. When you're thinking of users in a social network and you are trying to predict relationships between them, this is literally like the textbook example for graph neural networks. So obviously the original implementation followed that theoretical example, and they implemented a GNN. It had very high precision, which was a priority in this case. And essentially the model was doing really well, and it went on for a while. After about a year or so, we were trying to do exploratory studies to improve the model performance. And that's when we found a couple of interesting things. So the first interesting thing we found was that we could replace a good amount of the predictions with just very simple rules. So we could just use basic heuristics, and that was giving us pretty good predictions for a good chunk of the cases. And the second thing we found was XGBoost could cover majority of the remaining cases that weren't covered by the rule. And obviously that uses much fewer resources than training a graph, training a GNN with all of the node features and edge features and all the jazz. So this led to a couple of interesting lessons for us, for my team, and for me personally. that, sometimes even when your problem is a textbook example use case for a model type, your specific situation may not need it. And this can happen for different reasons. It might be that, your data is simply much simpler than needed, or maybe it's much richer and it already has, and it has enough information to be able to use a simpler solution. And the other interesting thing might be that your metric requirements and resource requirements might simply be different, right? So you may not need as complex a model to get the results that you are looking for. The other lessons from this were always revisit your model architecture choices and see if it still makes sense. In this case, we did have a model that was running pretty successfully, but one thing we noticed was as the user graph changes, GNNs require retraining, and that's not always feasible at the frequency at which it is required. So it's a good idea to always revisit your model architecture, see if those choices still make sense, and kind of loop back to that. The other thing, and this is I know the other lessons are also mentioned in this chapter, but this one particularly stood out to me, is that establishing baselines is really invaluable. In this case, it turns out that knowing that XGBoost or even like simple rule-based predictions can be useful, that tells us a lot, and we should be using baselines like that to evaluate our model choices. So that's a case study from me, and I'm going to pass on to Sharma, who will continue the discussion for this chapter.
Hey, thanks, Suchi. So I guess now we get to the part of the book that's a little bit more academic and has some theory behind it. So a couple of things that the book talks about in terms of giving, I guess, the reader a sense of what types of models exist. One of them is ensembling. I think this is a fairly standard textbook process, but from a industry point of view, I think it's useful to understand the higher level idea here. Typically, you deploy a linear model as a first case just to see what the data set is like and what the performances are. And then you move on to a slightly more complex model. Usually today, people jump to DNNs, or maybe a DNN is the second thing. But there is still a lot of value in these three ideas here: bagging, boosting, and stacking. And all three of them sort of combine the basic principle that your data is pretty rich and it can be trained for far fewer resources to get very good performance. So with bagging, the general idea is to create different sets of the same data, assume an independence on them, or rather between them, and train multiple models off of them, and then use that combination to give you an aggregate performance. This model is fairly fast to run because it's it's more or less just plain code. Typically, people use random forests, which are just decision tree learning processes, and these are really fast to run. But the con is they can degrade in performance simply because they're sort of like overfitting, because they try to understand different pieces of the data. And when you go through unsupervised methods, you might understand better relationships within the data. And this is just one approach that you might want to think about. Boosting is another classical ML technique where you train a series of models, and each subsequent model that you train is weighing the data on which your previous models did not work well on, and giving those models, those weights, a higher preference. So that way, the samples on which your model did not perform well is sort of scrutinized a bit more. And this boosting technique is something that is very popular, and it's part of a very, very popular package called XGBoost. If you go to Kaggle or other kinds of platforms and other case studies, XGBoost is predominantly used simply because it's just easier to intuitively understand where the performance gains are. And a little more of a complex technique is stacking, where you have possibly different models, and you try to combine them in some way, which you then use as a meta learning process. So all three of these techniques are a little bit rooted in the theory, and the book, for obvious reasons, doesn't cover them too much, but it's fairly useful to get a sense of these ideas. So, if you are somebody who's evaluating these techniques, you at least know that they exist. But you do have to go into a little bit of theory, for example, to understand why stacking works, and or how to combine them, how to have some stability over the outputs. Next slide, please. Okay, so like the theme of sort of developing software, tracking and versioning of your experiments is pretty important. So with code, given the deterministic nature, you typically use something like Git, and you kind of know that between Git commits, your code is changed. This is how the performance changes, and those types of sort of metrics can be teased out. But with models, it's a little bit different because you're not only tracking the code that's powering the model, you're also dealing with the entire data set. So it's important to understand what data you used to first check your baseline, and then make sure that those artifacts are reproducible, and make sure that you track those performances across training runs. Typically, an ML engineer or a research scientist will more or less pick up a bunch of data, put them in an S3 bucket, something like that, and then use additional tools. So one of them, I think, in the book was weights and biases that's mentioned, and that's pretty popular across the board these days. So you use that to kind of train your model, make sure that you have a copy of the metrics, then you kind of do this process over and try to understand what's happening. The book mentions a few things which are fairly typical to track. So loss curves, for example, give you a good sense of how much the model is learning. You can kind of understand the gradient of this graph to get a sense that things are going well. Occasionally, you'll see something weird, and then you'll have to go backtrack. And of course, there are other simpler ideas, like just understanding the performance metrics across, like if you have a classification task, you have accuracy metrics and things like that. And versioning also has a small problem when you're dealing with a lot of data. You don't have a lot of standard tools to use. I think typically these days you have FS packages, so basically they're file system replacements that can use Git to understand that a large binary blob has tiny changes within it, and then you can track them. So data versioning, I think, is an evolving process. Code versioning, I mean, the entire conversation started like basically a decade or two ago. Data versioning is just kind of getting into the picture that, oh, we should do this. I think if you go to like Hugging Face or other repositories today, you can kind of see them doing that with the model artifacts, where you have these massive neural networks and you have to kind of like version them. All right, next slide, please. Okay, and then the other practical consideration for developing models is how do you debug them? So given that with respect to software engineering, software testing is a fairly established standard, and most people know how to do it. ML models are similar, but they're also different because you still have to understand how the theory works to get a sense of what breaks down. So on the theory side, I think you'll have to deal with like you have to really go ask a subject matter expert. But if you're just looking at it from a software side, there are simple ideas that you can try as a practitioner, right? So for example, one of the things the book talks about is how do you overfit on a single batch? So this one is kind of interesting because you know that a model is supposed to overfit if you kind of give it all of the data and you kind of cheat a little bit. So if you are not able to do that, basically if you're not able to cheat, then you know something is off with the implementation or the data or your code, something like that. So typically when you write a unit test, you say that, given this input, I want this output. That's kind of similar to what overfitting on a single batch is. And then you have simpler ideas like, making sure you set the random seed, right? Like, so simple things like you run this code, you hit the run button several times in your Colab notebook, you should get the same output. So just making sure that these basic ideas is things that you can try from a software perspective. And I think you have to like kind of understand how much you can do that on the software side, and then how much you have to really understand other assumptions of the data, how much you have to do like data analysis to see if this data set is good for like the model you end up picking. So in terms of challenges, the really interesting thing is that ML models, if they're kind of in an in-between zone where you don't know how to interpret them well, or if they're not easy to interpret, they might fail silently, and you will never understand this until you see dramatic differences in your business output. Like, if you're tracking business metrics, like something even as simple as revenue, if you deploy a model that's going to affect it, there is a good chance that you will not see that until after a subsequent amount of losses has been sort of taken on. And given that ML models typically use data that is cross-cutting across the entire organization, you really have to understand every team's sort of like development process, what kind of culture they have. If you're working in a big company, you have to think about culture and those types of things. Like how do they deal with uh, like updates to their training pipelines and things like that. Next slide, please. Okay, and I think in the book, we have a couple of points about, and I'll just rush through the slide. So in the book, in terms of data training, we have like a couple of pieces. One is data and model, data parallelism. The other is model parallelism. So with data, you're sharding your data on multiple machines and training them and having some sort of synchronization process between them. And for model parallelism, your model is spread across multiple computers, and you kind of train them in that distributed fashion. I'll kind of skip over these details because you have to go and understand like the papers to see what people have done. But there are different ways to kind of implement distributed training. Next slide, please. Yeah, and this was a case study that's a project from my work from a while ago. So in the interest of time, I'll just run through this. So there were two main lessons here. One is baselining. The other one is making sure that you pick the relevant metrics. In terms of baselining, before you jump to a complex model, you should try to pick a smaller model. Make sure you're tuning that a little bit at least to see if you can get good performance. And then in terms of trade-offs, something as practical as the memory cost to load this model and keep it in memory, meaning if you have a bigger model, you need a bigger box. You can use that as one of your metrics if cost is a consideration. So you can kind of trade that, plot that, and then see if choosing a smaller memory footprint does not affect your final outcome. So if that's the case, then you have choices to make. Yeah, next slide, please. And I think I'll hand it off to Charles.
Yeah, we're talking about AutoML. So AutoML aims to automate the process of finding ML algorithms to solve real-world problems. There are two classes of AutoML. One is a soft AutoML, and another is hard AutoML. Soft AutoML is the most popular form. Like its most popular form is hyperparameter tuning. The goal is to find the optimal set of hyperparameter in the search space, and the popular method is random search, grid search, Bayesian optimization. You would input your training data and get a model output with this like black box kind of training thing. With hard AutoML, it's what if we treat the model components or entire model as a hyperparameter. It's also known as architectural search or NAS. The challenges with hard AutoML is that the optimizers are sensitive to hyperparameter tunings, hyperparameter settings, and the solution is learn optimizers. It can train on the same data set as the neural networks and train once on a set of existing tasks, then generalize it. The phases of model development typically starts with like before ML. You would try out heuristic, simple non-ML solutions, and then you wanted to iterate on the process. First, starting with a simple ML model architecture, like logistic regression, gradient boost, and optimizing the simple ML models. And the reason to do that is because if you pull a complex off-the-shelf ML models, it will be difficult to iterate on the ML models and improve the accuracy. Like if you have a complex model that's already 90% accuracy and you try to boost it up to 98% or 90, even 95%, that kind of small amount of boost would be difficult if you have a complex architecture at the beginning of it. And optimizing simple models, we can optimize either the objective functions, hyperparameters, features, and then we go with a complex model, try a more complex architecture, and repeat the step 2 and 3. Next up, I will be talking about offline evaluations. So when we start with model evaluation, we want to start with a baseline. We want to translate the model matrix to usefulness, and there's a need to establish a baseline first, because without a baseline, you cannot compare apple to apple. You can test your ML model against another model that generates output at random. For example, the book gave an interesting example where MLE achieved a 0.9 F1 score. But upon closer inspection, it seems that the task that he's solving has 90% positive class. So if his model just randomly output the positive class 90% of the time, the F1 score will be 0.9 anyway. And then another way is to represent simple heuristics for the other business problem in mind. For example, like decision tree, zero rule, or just based on plain observations. And the third one is like human evaluation. So I'll be going, and sorry, let me skip that. I wanted to talk a bit about what we do at my team. In my team, one approach that we often utilize for establishing the baseline is to pull off-the-shelf model without any fine-tuning and evaluate its performance as is on the task in hand. Another way we can do this is using AutoML with the input that you already have, and use that, evaluate the performance of the AutoML as the baseline of the model. Next, I'll be talking about evaluation methods. There are multiple methods that we can use to evaluate ML models, and it's critical that we have this in place in the CI/CD pipeline so that we are able to iterate on the ML models and improve on it. If you don't have something that you can measure, you cannot improve on it. So the first way we can do this is perturbation test. And how we do that is we add noise to the data set and test the model performance. In my team, we have this critical view of safety machine learning models, which is you are trying to predict the golden triangle in the gallbladder. Like, in order to achieve that, there are 3 requirements that you need to meet. One is only 2 structures can be clearly seen connected to the gallbladder, and the lower 1/3 of the gallbladder is separated from the liver to expose the cystic plate, and the hepatocystic triangle must be completely clear of tissue, allowing proper visibility. And our research scientists hand us an ML model to productionize it, but during testing of the ML models before productionizing it, I noticed that when I rotate or crop the data set, the performance of the model fluctuates a lot. And that's proven issue. And then another way we can do evaluation is invariance test, which is you perturb some of the features in the data set, and with the domain knowledge that you are not expecting any changes in the output with this perturbation. Another way is directional expectation tests, which differ into invariance tests. Certain changes to input should cause predictable changes in outputs. So back to the critical view of safety. When I was like patching, like applying black patches to the images, I noticed that the model is only looking for gallbladder instead of the 3 criteria that I was mentioning just now. So that's something proved to be problematic, especially you don't want to deploy a model like this in healthcare. So this is yet another example that evaluation method is really important in production. And then the next one is about model calibration. The idea is to compute the probability that given a label, label equals to 1 given the model probability. If the predicting model says there will be 1,000 clicks in production, if it's 900 clicks, then it's not properly calibrated. And then there's like 2 more methods about prediction confidence, which you can evaluate via softmax and also slice-based evaluation. The book talk about Simpson's paradox, and that there are like 3 approaches to that. One is heuristics, error analysis, and also slice finder. I won't be covering that in detail over here. I want to talk about how things go in the age of Gen AI. So evaluation of LLM can be categorized into 3 major groups. One is knowledge and capability evaluation. I won't be focusing in this slide because I have 2 other slides that covers that. The second approach is alignment evaluation. Why do we do alignment? The training objective of LLM, which perform the next word of prediction or determine whether 2 sentences are contextually related, are not necessarily in line with human values. LLM may generate undesirable content like biased, toxic, privacy sensitive biased content, and also unfaithful content like fabricated contents, misinformations, hallucinations. Unfaithful contents like this, it affects the trustworthiness, but also application in professional fields like healthcare and law. And how do we evaluate for this alignment is through reinforcement learning from human feedback, PPO, DPO, and KTO. I will talk at high level about this PPO, DPO, and KTO, but you can click on these links to learn more about it. So PPO aims to maximize the expected reward while preserving large policy updates. And it takes in input states and rewards from the environment, and it outputs actions to be taken in the environment. Whereas DPO, it optimizes policy based on human preference using a binary classification of objective. So over here, I provide this example of prompt, worst completion, and better completion. That's the input that it's taking from the environment and also human preference feedback. The output is the actions to be taken in the environment aligned with the human preference. KTO is yet another approach that comes out by Stanford. It aligns model by maximizing the utility of LLM generation based on prospect theory without requiring detailed preference pair. It takes the input of LLM outputs with binary labels indicating desirable or undesirable outcome. And the output is LLM generations aligned with simplified human utility functions. KTO, it's more generally used because of its ease of input, like more user-friendly input. And the third part of evaluation for LLM is safety evaluation, and that's robustness against adversarial prompts. So the adversarial prompts crafted to mimic plausible user errors like typos or synonyms. It aims to evaluate how slight deviations can affect LLM outcomes while maintaining the semantic integrity. These prompts are then employed in diverse attacks, including sentiment analysis, in diverse tasks, including sentiment analysis, NLP, natural language inference, reading, comprehension, machine translation, and math problem solving. There's a case where DeepMind, it it figured out that if you repeat the word poem like 1,000 times, then ChatGPT will start spitting out training data. That was like early this year, and the issue has since been fixed. So when developing LLM, we need to do it carefully in the pillar of these three groups. So I'll be talking about the first part, which I skipped just now, evaluation for LLM. There's a difference between evaluation for LLM versus the system itself. Large language model out of the box, it performs various tasks such as chatbot, natural entity recognition, text generation, summarization, Q&A, sentiment analysis, and translation. And there are a bunch of standardized benchmarks. That's like MLU, GL, like Glue, Superglue, Hella Swag, Truthful QA. I won't be going into details of all of these. You can click onto this if you are interested. And on the Gemini paper, they also have like benchmark their models against this matrix. So for a large language model system, why do we need this separation? It's because LLM immediate applicability off the shelf are oftentimes constrained for specific requirements. And we oftentimes need to go in and fine tune LLM using domain specific data set, RAG, etc. Research scientists need to ensure that they are utilizing the appropriate prompt templates, implement effective data retrieval pipelines, and when fine tuning properly, consider the model architecture. To evaluate these systems, we need to compare the performance of the system against ground truth data set. And this becomes tricky because getting this ground truth data set on a wide, diverse range of tasks is expensive. There are a few ways to perform offline evaluation. One is through eyeballing, and this is mostly employed when you are doing like chain of thought prompting and you wanted to just quickly evaluate your prompt quality. There's also utilize a powerful large language model like GPT-4 to generate a meaningful synthetic evaluation data sets. And this usually requires human in the loop. There's also large language model guided evaluation, which is actually using LLM to evaluate LLM. And how you do that is that you ask LLM to produce an output. You get the LLM to score the output of these results. And that also requires human in the loop as well. There are a bunch of existing frameworks that supports this. There's OpenAI Evals, Vertex AI Studio, Language Model Evaluation Harness, Uptrain, Prompt Bench. All right, I will hand it over to Suchi to talk about the discussion questions.
Sorry, yeah, I think Sharma is supposed to go over the.
Oh, yeah. Yeah, so in terms of discussion, it seems like most of this chapter is about baselining and understanding how your models work. So here's a couple of topics to think about. So for LLMs, we have human eval. So that might be something interesting to understand. Most people tout models on leaderboards. So you could probably talk about that. And AutoML was interesting because it was a big deal a while ago. But now with a lot of these neural network frameworks, how do they fit into your work? And in terms of your own personal work experience, yeah, if you have model architectures to talk about, maybe you could go over the trade-offs and the choices you've made. Yeah, that's about it. Thank you for this presentation, and I guess yeah, you guys can sort out into breakout rooms.
Yeah, can we go back to the discussion question slide so that people can see it, and we can ask. Can the host do the breakout rooms?
Yeah. So thanks for joining the YouTube viewers. We're going to end the stream for you guys, and for the Zoom participants, just stay on and we'll put you in breakout rooms. Thanks a lot.